All right, guys. In this lesson, we are going to talk about section 5.1, the fundamental trigonometric identities. We are going to put these identities on this little graphic organizer that I've provided in class. I will link it on our Canvas page in case you wish to print it out. But rather than put them in our notebook, we're going to put them on a separate paper. It's kind of organized really pretty. So, and then we'll come back here and we'll work some problems. Okay. So here are some of them. We already know quite a few of these properties. And the way we're going to kind of maybe briefly discuss on here how some of these properties come to be, but I'm not going to go in crazy detail. We did take quite a bit of time in class to go through a lot of justification as to why things were. But just to save us time here on the video, here's the properties. So you've got your reciprocal identities, which again, this is not new. Cosecant is 1 over sine. Secant is 1 over cosine. Tangent or cotangent is 1 over tangent. We also have these things called the Pythagorean identities, and we spent quite a bit of time in class trying to prove these. Essentially, they come from the fact that on your unit circle, the y value is the sine, the x value is the cosine, and the radius is the value 1. And based off of the properties that we learned about the unit circle in section 4.3, we were able to create a triangle. And we used Pythagorean theorem, a squared plus b squared equals c squared. It came out to be x squared plus y squared equals 1 squared, and x is cosine, sine is y. So we were able to replace those values. In order to get these guys, all I have to do is manipulate this equation. So to get this equation that you're seeing right underneath it, if I just divide this entire equation through by cosine, cosine divided by cosine cancels, makes 1. Sine over cosine is tangent. 1 over cosine is secant. So you're able to create these other ones. We can create this last one by taking the original and dividing through by sine. If you divide by sine, cosine over sine, cotangent. Sine over sine, 1. 1 over sine is cosecant. So we're able to just make these properties. If you forget how to prove it, not a big deal, because we need to be able to apply them. That's kind of the main focus. Proving is something else we'll kind of talk about, but really, if you can apply them, then you can prove as well. So anyways, okay, we got a couple more. So these ones we also should already be familiar with here in the middle. Tangent, sine over cosine, cotangent, cosine over sine. So again, that's not new. The ones at the bottom come from the idea of the fact that sine and cosine are essentially the same thing. It's just that they're shifted over from one another. So we've talked about the fact that they have the same height, they have the same period, they have all the same features, except sine goes through the origin, cosine goes through its maximum on the y-axis. And so they're just shifted over compared to each other. These cofunction identities, you're going to see that type of thing. This is like a horizontal shift of pi over 2, so that we're lining it up. They've also included here a little reflection across the y-axis to get these little cofunction identities. So that's really where it comes from, is some transformations. So sine is pi over 2 minus theta, sine of pi over 2 minus theta is the same as just cosine of theta. So you're able to simplify things. If you had something in this format, it's just cosine of that angle. So it just makes it more simple. Okay, and then we've got one more little section, these even odd identities. If you guys recall back from, I believe it was chapter 1, if a function was odd, then you would have been able to see that f of negative x was the same as negative f of x. Sine is an odd function, so it follows that property. Sine of negative x is negative sine of x. It also, if another way you can tell that it's odd is because of looking at the graph of it. The graph of it looks the same upside down as it does right side up. It's odd. Cosine is not. That's why you're seeing this property looks different. It's not a miswrite. It is cosine of negative x is positive cosine of x, and that's because cosine is even. It is symmetrical across the y-axis. And the property that we did algebraically back in chapter 1 was that f of negative x was equal to positive f of x. If they're even, that's what we had. And then tangent of negative x equals negative tangent of x. Tangent is odd, just like sine is, so it has a similar property. All right, so that is the properties in a nutshell that we're going to start with. We will add more properties in a later section, so look forward to that. But for the time being, we're going to just start with these ones, and we'll end up working our way up, okay? So I'm going to go back to our notebook paper. We're going to work a few examples, see how this goes. If I need to make a second video, then I will. It just kind of depends on how long it takes us to get through these. Try not to make my videos longer than 20 to 25 minutes maximum. And honestly, that's probably still long. So anyways, here we are, fundamental identities. And the first question, they said, if find sine of theta and cosine of theta if tangent is 5 and cosine is greater than 0, so cosine is positive. Now, this is technically not really a new thing, but we haven't done one like it in our notes. I don't think we've had one on a worksheet somewhere. So anyways, I just figured it doesn't hurt us to see one of these all together, just to make sure we're on the right page. Okay. So they said, find sine and cosine if tangent is 5. Now, there's a few different ways you can go about this, but I'm going to start with that solid concrete number that they gave us. They said tangent of theta is 5. Now, I want you to remember 5 is the same as 5 over 1. So I can look at this as a ratio. And remember also from SOHCAHTOA that tangent is opposite over adjacent. So I can use that to my advantage. Also knowing that tangent is positive and cosine is positive, then if they're both positive, that forces me to be in the first quadrant. So just to kind of get a little picture started, if cosine is positive, right, we're on the right side of this guy. If tangent is also positive, that means y would have been positive as well. So it's got to be over in here. Okay, now I'm not going to make this 100% perfect. I'm just going to draw a little triangle, make this be theta. Okay, and I'm going to label it as opposite over adjacent, so 5 over 1 like that. And really, just to get the rest of the values, all I need to do is find the hypotenuse, and then I can give the sine and the cosine. So we're going to use Pythagorean theorem. 1 squared plus 5 squared equals, we'll just call it h squared for hypotenuse. 1 plus 25 equals h squared. 26 equals h squared. Don't forget to square root it, guys. I don't know how many of us forget that step, but the hypotenuse here is the square root of 26. So in order to give my answer, we're going to say sine. Again, that is opposite over hypotenuse. That would be 5 over square root of 26. Now remember how I say this is an okay answer to leave. However, you also can rationalize the denominator. So if you do, you would multiply top and bottom by the square root of 26. And that would have given you 5 square root 26 over 26. Both of those are valid, okay? Cosine, we're going to have a similar situation, except adjacent over hypotenuse. So 1 over the square root of 26. Again, if you multiply top and bottom by the square root of 26, it gives me square root 26 over 26. So either one, you can leave it rationalized or not. Either format is fine. Okay? All right, moving on. So next type of example you're going to see is you should kind of sort of recognize this as something similar to the cofunction identity. It's not exactly the same. So they told me that cosine is 0.34. Then they said find sine of theta minus pi over 2. Now you might just be tempted to straight up use the cofunction identity, but I want to bring this back and show you. it's not, the problem I have on the notebook paper is theta minus pi over 2. This is pi over 2 minus theta, so it's not the same. And you can't just swap it and call it a day. You do have to think about this a little bit. So it's actually going to use multiple properties in order for us to do this. And I'm going to try to justify them as we go, just so that you're understanding what properties I'm using along the way. Okay. Okay. Here we are. So I'm going to start out with that sine of, theta minus pi over 2 that we are working with. And the first thing I'm going to do is, I know that the negative is not with the right thing for me to use the cofunction identity. The cofunction identity wants the theta to be negative and the pi over 2 to be positive, which means I have to manipulate these signs. If it's that simple, where the only thing is I just need to change both signs, it's not too bad. What I'm going to do is I'm going to factor a negative out. So you're going to see this. It might look a little funky for a second. Just taking a negative out so that I can change these signs. Okay. Again, all I did is factor out a negative, so I'm going to put that just as a note over here. Factor out negative. Okay. Okay. So the next thing we can do is we can change the order, because addition and subtraction, they're commutative, or addition is commutative. So what I can do is change this order, but I need to keep the signs with them. So this is going to be pi over 2 minus theta, which is more like what I want, but now I have this negative in here. Well, if you remember, we had an even odd identity. Remember how we had, if you had sine of negative x, it's the same as negative sine of x. I can pull that negative out using the odd identity, even odd identity. So really this is negative sine of pi over 2 minus theta. Again, this was the even or odd identity. And then the last little bit is, now that I've got it as pi over 2 minus theta inside of that sine function, remember how we said sine of pi over 2 minus theta is cosine. Didn't they tell me what cosine was? Cosine was 0.34. So really this is negative cosine. I'm going to write this out just to make sure that we're a little clear-ish, clear as mud. We changed this sine of pi over 2 minus theta into cosine because of your cofunction identity. And if cosine is 0.34, then this is negative 0.34 by using substitution. Okay? All right, if you're wanting to justify this one back here just for fun, this was the commutative property. So we switched the order. But that is the commutative property, in case you're wondering what's the mathematical justification. Okay, that's that. We got it. Negative 0.34. All right, we are going to simplify. I like these. I think these are kind of fun. Once you get the hang of it, they feel very, very puzzly. And once everything works out, it's so satisfying. Because you take something from a pretty ugly expression and you make it pretty. So I really do enjoy these types of problems personally. And I think you guys will like these better than some of the ones we've had lately. So we'll see. Okay. It may take a second to get used to it, but the idea is we're going to force to use these properties. Now, what I'm noticing is we have a sine cubed, we have sine, and then cosine squared. Now, we have one set of properties that uses exponents. That's the Pythagorean identities. Now, every time you see exponents, it doesn't mean that you're going to use one of these, but it is very highly likely. So since I see those exponents, I'm going to see, is there a way for me to figure out how to use sine, maybe one of these Pythagorean identities? Now I'm noticing this is using sine and cosine. okay? Which would lead me to think I'm going to try to force to use this one a little bit. So let's see what we can do with this. I do see that they both have sine in common, okay? It's similar to if you had a situation back in like Algebra 1, where in Algebra 1, if you had like, say that you had like x cubed plus x times y squared. Do you remember how you could factor out that x and I could take it, make it x squared plus y squared? You could undistribute or factor that out. I'm going to do a similar concept right here, okay? I'm going to see how they both have a sign, just like my last thing just had an x in both terms. I'm going to take the sign out and look at what happens. If I take out a sine of theta, then what's left would be sine squared theta plus cosine squared theta. And sine squared plus cosine squared is 1. So I can replace this whole set of parentheses with just a 1. This would be sine of theta times 1. And that's just sine of theta. So we took an ugly expression, simplified it down to one trig function. I feel like those are satisfying. Okay, let's try another one. This one's a little weirder. It's got some multiplication happening and also division. You see this little fraction bar. So let's see what we can do. What I'm going to start out with is FOIL, because I do see that these are separated with parentheses. I also am noticing that they are exactly the same except that sign. And that was, I recognize that as before it was factored, it was a difference of squares. And those are usually pretty simple to work with. So let's just see what this works out to be. I'm going to keep those brackets there for the time being. Secant times secant would make secant squared of, x. I wanted to put a theta. Secant squared of x. Secant of x times a negative 1, negative secant x. 1 times secant of x is plus secant x. 1 times a negative 1, negative 1. And again, all that's being divided by sine squared x. All right, now look at what happens here in the middle. Negative secant plus secant, gone. So really, this is secant squared x minus 1 divided by sine squared x. Now, I'm seeing secant squared and then a 1. And to me, that's bringing back this vibe of Pythagorean identities because I'm seeing a squared trig function and a 1. And so I'm going to go find, where do I have that? Well, this is not exactly in the correct format. This is 1 plus tangent squared equals secant squared theta. But I want you to think about, how could we manipulate this guy and use it to our advantage? Well, if I want this to be secant squared minus 1, let's think about how I can manipulate this. I could subtract 1 on both sides. That would leave you with tangent squared theta equals secant squared theta minus 1. Okay, so if secant squared theta minus 1 is equal to tangent squared theta, then this top part is really equal to tangent squared. And that's being divided by sine squared. Again, the reason I could do that is because of that situation from that Pythagorean identity where I could subtract 1 on both sides. I turned it into secant squared theta minus 1 right there. So I could replace that with tangent squared. All right, you might be thinking, all right, I can't do anything else, but you can. Tangent can always be written as sine over cosine. So I want you to see this, sine squared x over cosine x, or squared x, excuse me. So tangent squared can always be written as sine over cosine. And we're dividing this by sine squared. Dividing is the same as multiplying by the reciprocal. So I want you to see what's going on here. Okay, tangent I turned into sine over cosine, divided by, right, keep, change, flip, 1 over cosine, or 1 over sine. And the sine squareds cancel out. just like that. So I'm really getting something more like 1 over cosine. But it's not great to always leave these, unless they tell you to leave it in terms of sine or cosine for some reason. It's better to write it using the reciprocal identity. 1 over cosine is the same as secant. So secant squared x would be your answer. Okay. I'm going to try to do one more in this video. And in the next video, we will talk about solving. Okay, so we'll kind of keep it separated out this way. This next problem is a little bit time consuming or a little bit tricky, but we're going to try to make it work anyways in the time that I have left. Okay. All right, so we are looking at here cosine x over 1 minus sine of x. And that is equal to sine x over cosine of x. Okay, now your first instinct might be to change sine over cosine to be a tangent. Here's my problem with that is you can't do much past that point. You would change it and you would feel stuck. So here's my suggestion instead. I want to see if I can combine these fractions and then see if there's anything else that happens from there. In order to combine the fractions, though, you'd have to have common denominators. The easiest way to do that is to take this fraction and multiply top and bottom by the denominator of the other one. So this is kind of what it would look like. Normally, I wouldn't show all of this out, but you would throw everything in parentheses, and I would multiply times cosine x times cosine x. Okay? Over here, I'm going to take this other one, and I'm going to multiply it, top and bottom, by the denominator of the first one. So I'm going to do times 1 minus sine of x over 1 minus sine x. Okay. You don't have to draw the bar in between there. You can or not. Just kind of depends on you. Okay. But what this is going to do, I want you to see this. You see how this is going to make 1 minus sine of x times cosine of x, right? Cosine of x times 1 minus sine of x. It's the same thing on the bottom. And since their denominators will be the same, then we'll be able to add their numerators. Okay. So from there, I'm going to make this top part be cosine squared x, cosine times cosine. This next one, I'm going to go ahead and distribute this negative sine of x, because that's really what's happening here. Negative sine of x times 1, negative sine of x. Negative sine of x times a negative sine of x makes a positive sine squared x. So this negative, he belongs to this sign, okay? Keep that in mind. So when you are multiplying, when you're taking this whole thing and distributing it, the negative has to go with them, okay? All right, that's the numerator. Now the denominator, once you combine them, because they've got common denominators, I am going to just leave this separate. And I know that feels a little weird, but I am going to leave this separate for now unless I see a reason to combine it. Because at some point, it's possible that stuff will cancel out. And so if I just leave it factored for now, it makes it easier. All right, in the numerator, I want you to see this. Do you see the cosine squared plus sine squared? If you recognize that straight away, then feel free to go ahead and just replace that value with a 1. Sorry. But I'm going to change the order just so that for the sake of your notes, you kind of see a little bit more clearly what I did. Okay, sine plus cosine, right, squared. Cosine squared plus sine squared is 1. So I'm going to replace this bit, the squareds on top. I'm going to replace that with just a 1. So it becomes 1 minus sine of x up in the numerator. Now, do you see here how I have 1 minus sine of x on the top and on the bottom? Okay, that can cancel out and leave a 1 in the numerator. Boom, gone. So really, this is 1 over cosine of x and 1 over cosine of x is in fact the same thing as secant of x. Ta-da! Little tricky, right? You get used to stuff. So like I said, I know your impulse might have been up here to go ahead and change this to be tangent, but if you did, you wouldn't have had anywhere to go from there. If that's all you can do, then that's probably not the right path to take. You're going to want to be able to simplify it down. Now, guys, the answers are the questions that I assign you are odd numbered questions. So you can check yourself in the back of the textbook, but you should be showing me work like this. There should not be this stuff going on in your head. I need to see the work so that I can know that you actually found out how to do this and didn't just copy an answer down, because work is required here. Okay. All right. Anyways, in the next video, we will cover solving, and then you will be all done with this section. So awesome. I'll see you in the next one. Bye.